Good morning. I am Bachelor from the Federal University of Rio de Janeiro. I am a nuclear engineer, but I am more known as Lynn's wife. And I presented 3 applications of Hydrus 1D that we had in the last years in collaboration with Spain and Victoria Ottoni. So the first study case is a non-waste disposal. My field is more do risk assessment of mining sites that we have natural radionuclides occurring. The other one was simulation in a municipal landfill to see the best cover. And the last one, the application for a safe assessment of low-level radioactive waste repository after the accident of cesium-137 source. Okay. So the first case is a mining site in Amazonia, inside the forest. We have an open pit mine, and we have crushing the rock, separation and concentration. We use pyrometallurgy, and these concentrate a lot the natural radionuclides. And the regulatory body requires that we present a safety assessment to see if it's safe or not. And normally we need to use only natural barriers, not engineered barriers in that case. Here you have the production, and here is the extraction of tin and niobio and tantalum. And this waste that we call these bags are put in a huge landfill in layers. Okay, you put, for example, 2 meters of these legs and 50 centimeters of soil in layers. So the non-waste, we use natural barriers, as I said, because we use to do the safety assessment for long geological times. Until now, the regulatory body didn't decide if we run for 10,000 years, that will be the new glacial era, or the peak of those. So here we decided to present for peak of those, and we have normally 6 meters of these legs and the soil, compacted soil, that is basically a clay soil. We model the uranium decay chain. Even in Brazil, we have 2-3 times more thorium, natural thorium. The thorium is not too mobile, so it's more important to model uranium decay chains. So we have the more important chains that uranium-238, 234, thorium, radium, and lead. And during the process of this lead, the natural equilibrium is cut, and normally lead evaporates, and we stay more with radium and uranium. So we have 6 meters layer of slag, after 5 meters of red clay soil, and here is our aquifer. One characteristic of the Amazon forest that we have a huge precipitation, okay, around 2.5 into 3 meters per year, a huge evapotranspiration also. That time when we did this calculation, Hydrus didn't have hard dips of elements in the cold after they aggregate, and we are using now directly with Hydrus. And we calculated the recharge, and we suppose the equilibrium sorption. Okay. And here we were doing some sensitivity analysis, supposing when we have equilibrium or no-equilibrium in the different layers. So here is the waste layer. We can see here the equilibrium. And the other ones, what happened? We have lower peak, but earlier, appears in years. So appears before 20,000 years. Here is in the Vadel zone, becquerel per cubic meter. We have higher peak here, but of course before. And we took uranium because we saw that was the most relevant in our case. And here in the groundwater, the safety assessment supposed that we put a well 100 meters away from the disposal site, and a population will use this water to drink and other things. So, and here, finally, we did our safety assessment to see equilibrium and preferential transport. So what happened, at least for uranium and the other ones, the same, well, within the peak before, but basically in the same level. So for the regulatory body, we could prove that it's not important in that case if we have a preferential flow or not. When we will see peak of dose, if the regulatory body can define some time, perhaps can be more important to see that we arrive earlier or not. So the other application was a municipal waste landfill, and was to simulate the water flux in the cover layers. And the program was set up with the first sub-landfill, I will show you how, and compare
As elephants, no?
the different covers that can use to diminish the infiltration of water in this landfill. So here we have the size, the location that's close to Rio de Janeiro town, and is divided in 4 sublandfills. Here is the kind of waste. Here you can see that we can collect the shade, etc. And they decided to do in cells. So this one now is ready, and they would like to know the best cover to put. Okay, and here is the view we have to place. So in this landfill, we need to meet the requirements of a Brazilian standard. We have a central treatment station for the leachate. We collect also the biogas and generate electricity for the population in the surrounds. We have a treatment unit for waste from a hospital. We need first to incinerate and treat. And also we have industrial wastes, not municipal. That is put. So this is the total area of the landfill. This is the total amount of the residues. And here is the one that the study was performed and the program was set up. So the first scenario we run is to set up the program. So we did only one of the cells, that was the sublandfill 1, and we set Hydrus to have the same or close to the same measured things. And after we did the performance with this data and spending for the 4 cells, that is the real case, okay? And for the 12 hectares. And here, put 30 centimeters of a fine texture soil, here coarse special gravel, compact soil. And here we variate a little, first with 30 and after 60. And here is to see which one will be more efficient. And also, which kind of vegetation to put on the top of the compact soil, grass or some local vegetation that is Brachiaria undicola. And here we have the vertical distribution when you have the thick roots, medium, fine, and here the total. And here we had the effect of the vegetation of a final layer. So here when you put grass, and here the brachiaria. So you could see that if you have only compact soil, here is the amount of water that we can have inside the waste layer. Here when you have a capillary barrier of 30 centimeters, here 50 centimeters, here when you put the grass, and here the brachiaria. So we could see that the best option to use as a cover was the natural vegetation of the place. And that will be used for the whole land. And the last application was the radioactive waste repository, which 6 years we needed to redo the safety assessment. So in '87, we had an accident with a source of cesium that spread over a town, was a salt and melted because of the rain. And basically the waste generated is soil contaminated with cesium. So we put in drums, and here is a near surface repository. It's different from the previous one that was presented. That you can see is just 50 centimeters inside the soil, and it is like a box of concrete. Inside we put these, we had some containers and some drums with waste. So first of all, we performed the calculation just to see the cover that we have. Here is the soil, but we have here 20 centimeters of concrete, 50 centimeters of soil and grass. So we calculate with the weather data using hard leaves for 10 years, the precipitation, potential evaporation. And after, we imagine that the concrete stay fresh from 0 to 100 years. After we have some degradation, especially in the hydraulic conductivity, and more degradation between 200 and 400 years. And also we tested here two root different distributions, constant and sloping. And here we have these infiltrations we assumed is 10 times more, 10 times more. Here we have the cumulative bottom flux, and here how we have the water going inside our repository. And after, we calculate the transport of cesium. So as I said, we have here the infiltration, we have like a concrete box. Here 20 centimeters of concrete, the vadose and the aquifer. Here the vadose we calculate for 4 to 5 meters because of the water table fluctuation. We measure all the hydraulic properties of the different layers. We obtain the KD for each layer. And here, first we see the concrete, just at the end of the concrete, how was the cesium transport. And we have these 3 humps because of the infiltration, but also here because of decay of cesium that is close to 30 years, the life. And here, just after the concrete layer, we point the 3 observation points, 10 centimeters under, 20 and 30. And we can see that is basically closer to zero. So here, when we have no plume, even in 400 years. So that, and we compare a lot of results we had here to set up the problem with the measurements, local measurements. And that's all. Thank you.
Thank you. Any questions? Okay, well then the next speaker.